Hello, good day. I am Chiamaka Okafor from the Florida International University in Miami. Welcome to my poster presentation titled Bioresorbable Alloy Design for Improved Electrochemical Degradation. Bioresorbable alloys are those alloys that when implanted within the human body, they serve their function, and after some time, say 6 months or 1 year, they can degrade without posing any harm to the human body. Magnesium alloys are bioresorbable. However, they suffer from very fast degradation rates and non-uniform degradation. Alloying is an effective way for improving the biodegradation behavior of magnesium alloys, and it is important that we alloy with elements such as calcium and zinc, which do not pose any threats to the human body. As we all know, there are over-the-counter drugs. As we all know, there are over-the-counter drugs of zinc and calcium. In this investigation, we look at magnesium zinc calcium alloys, and we incorporate hydroxyapatite and gadolinium elements to see how they affect the degradation behavior. Elements under investigation are tabulated here and are denoted as MZC, NOBCChE, and the NOBCChE. XRD and SEM analysis were carried out. EIS analysis, which is electrochemical impedance spectroscopy, was carried out in phosphate buffer solution. Biodegradation rates were determined by semi-static immersion test. This test was carried out in an incubator. The medium was Hank's balanced salt solution. We observed that as we increase the zinc percentage from here to here, we could see that there's 1 zinc for MZC and 3 zinc for MZChE, that there is an improved reduction in grain size. And addition of hydroxyapatite showed some kind of layer during the immersion test, and which seemed to improve the decrease in degradation rates. The addition of gadolinium did not really keep the grain size reduced. There was a little bit of increase, and the amount of secondary phases present more compared to the other two alloys as shown in this image. And we also found out that the large amount of secondary phases present increased degradation rate because the secondary phases could begin to act as cathodic pairs, and this will cause pitting. Also, generally, we found out that the MZC alloy had the lowest degradation rate as tabulated here, and we could also see that the parameters from the EIS Nyquist plots are represented here, and it also had the highest resistance, which is a parameter. It is directly related to the degradation rate. And we also noticed that it had uniform degradation, as we could see here, compared to the MZCchE, which had pits. In conclusion, proper control of secondary phase formation, both by alloying elements and by alloying percentage, is required for uniform degradation. These are some of the references used. And I want to acknowledge the Mechanical and Materials Engineering Department of Florida International University, the Advanced Materials Engineering Research Institute, and the Florida Center for Analytical Electron Microscopy. Thank you.